To model the physics of molecules, computational chemistry builds wavefunctions using the Slater determinant. Because a determinant mathematically forces the state to change sign when two electrons exchange positions, it successfully satisfies the Pauli exclusion principle. While raw determinants reliably map this required antisymmetry, they harbor a severe computational flaw. They suffer from spin ambiguity. This conceptual interface illustrates the problem. A single determinant is a reliable eigenfunction of the SC operator, calculating a definite spin projection, ms. But it's rarely an eigenfunction of the S² operator. The total spin remains undefined, contaminated by competing states. Satisfying the Pauli exclusion principle is only the baseline requirement. A valid quantum simulation cannot proceed without wavefunctions that possess a pure, cleanly defined total spin identity. This vector cone diagram shows why vertical projection, ms, does not equal total magnitude, s. ms is an accounting metric measuring the alpha-beta imbalance along the z-axis. But the physical S vector can possess multiple different overall lengths while maintaining that exact same vertical projection. The total magnitude, S, is the critical quantum number. It dictates the overall physical multiplicity of the state, defining whether a molecule is a singlet, a doublet, or a triplet. Relying solely on ms parameters leaves the physical state of the molecule unresolved. To lock down the correct total spin, the software requires a higher-order mathematical structure. This diagram illustrates a baseline closed shell scenario. When two electrons with opposite spins pair up inside the exact same spatial orbital, they automatically form a pure singlet state where both S and ms equal 0. For entirely closed shell molecules, the raw Slater determinant happens to define the total spin correctly. The computational modeling at this level is trivial. Here we have a side-by-side comparison of a more complex open shell system. We place two electrons in two different spatial orbitals, one spin up, one spin down. The ms projection is still 0. Intuition suggests this is another singlet. But this specific orbital occupation is ambiguous. The two electrons can couple their spins to form a singlet state, or they can couple to form a triplet state. The standard determinant for this configuration is mathematically comprised of a 50-50 mixture of both singlet and triplet characters simultaneously. Open shell systems render raw determinants mathematically inadequate. Feeding them directly into a simulation injects severe spin contamination into the results. The mathematical solution to this contamination is the configuration state function, or CSF. This graphic demonstrates the CSF's primary function. A CSF is a spin-adapted linear combination of Slater determinants, designed specifically to filter out contamination and extract a clean state. This visual maps the filtering process. The CSF operates like a mathematical prism, physically splitting the mixed determinant into its constituent pure spin states. Looking at the top track, subtracting two mixed determinants forces destructive interference, cleanly stripping out unwanted triplet character. To isolate the pure triplet state, the formula relies on addition. Adding the exact same determinants forces constructive interference, amplifying the triplet character entirely. This chart explains a rare exception for high spin states. When the spin projection ms equals exactly 1 or -1, the overall S vector is mathematically forced to match. These specific states bypass complex mixing because they are bounded automatically as pure triplets. By utilizing precise constructive and destructive mathematical interference, the CSF upgrades the original wavefunction, ensuring it acts as a true eigenfunction of both the S² and Sz operators. The transition from theoretical physics to applied computational software requires strict structural integrity, particularly for multireference methods like configuration interaction and CAS-SEF. This diagram shows the core architecture. Combining massive basis states requires strict guardrails. Evaluating raw determinants unknowingly pulls singlet and triplet characters together, irreversibly contaminating the results. CSFs prevent this failure. Because every individual CSF block is pre-verified, the software cannot accidentally inject contamination. CSFs are the exact required language for any algorithm tasked with cleanly targeting specific excited or open shell states. This graph maps how CSFs dictate the outcome of a physical event, detailing the energy curve as a hydrogen molecular bond stretches and breaks. At stable equilibrium in the energy well, the molecule is safely described by one closed shell singlet configuration. As the bond stretches, it acquires diradical character, requiring a second singlet configuration. This multireference equation manages the stretch, strictly locking every mathematical term to a singlet state. If spin adaptation is omitted here, raw determinants will allow triplet character to leak into the calculation. The simulated energy curve will collapse, yielding physics that do not match reality. Configuration state functions are the indispensable architecture of computational chemistry. They are the critical mechanism that forces the mathematics to correctly simulate the true quantum behavior of the physical